Hello, Calculus! These are the video notes for optimization. So in the intro, we just want to understand that optimization is essentially a scenario where you have a quantity that you would like to minimize or maximize. In general, you're going to have conditions or restrictions on the values that this quantity can take, such as cost or size or dimensions, that kind of thing. We have a strategy where we're going to introduce our variables and draw a figure, determine what quantity needs to be minimized and maximized, and write a formula, write any supplementary equations related to that quantity, and then identify the domain restrictions if needed, as well as locating a maximum or minimum using the extreme value theorem or by finding critical values. So our first example is an area question. We're going to construct a rectangular garden using a rock wall as one side of the garden and wire fencing for the other three sides. Given 100 feet of wire fencing, determine all dimensions that would create a garden of the maximum area. So here we have our rock wall. And then we're going to have 3 lengths of fence. And we know that altogether we can only use 100 feet. So this is an example of a restriction or a constraint. Now we need to define a variable that applies to the problem. So we are trying to determine the dimensions that would create a garden of a max area. So we'll call one of the dimensions x. Well, since the figure is rectangular, we know that opposite sides are congruent, which means that this is also x. Now here's where the supplementary equations come into play. The third side is not necessarily the same as the first two sides, and we don't have any wording relating the sides together where like it's twice the size or 3 times the size. So we're just going to call this y. For the perimeter, we know that 2x plus 1y has to equal 100 feet. Well, that means that y is the same as 100 minus 2x. With this in mind, we can write the formula all in terms of x instead of having an x and a y. Now we're ready to maximize. Since we're trying to do maximum area, our actual objective function is a equals length times width, or in this case, area equals x times 100 minus 2x. So let's take the derivative of the area. The derivative of this equation is 100 minus 2x plus x times negative 2 or 100 minus 4x. In order to locate a minimum or a maximum, we need to think of some restrictions. So let's restrict our domain. What values of x are possible? Well, the smallest value of x that would make any sense is 0. You can't have a side length of anything less than 0. And then since I'm restricted by my perimeter being 100, you could technically put all your fencing on one side. You just wouldn't get the job done. So we've got a domain restriction where x has to be from 0 to 100. And so using the extreme value theorem, I know that 0 and 100 represent potential minimums and maximums. And then I also know that the critical value, when the derivative is equal to 0, represents a minimum or a maximum. So let's finish solving for x. Over here, we should get x equals 25 feet. Well, if we think about it, if you make this side length 0 feet, you're going to have an area of 0. If you make this side length 100 feet, actually we should probably say that the max is 50, since we're guaranteed to have at least 2 x's. But either way, if you make that 50 feet, you're still going to have an area of 0 because you can't enclose the space. So these endpoints represent minimums of the function. That means x equals 25 probably represents the maximum area. So we'll say that the dimensions are 25 by 50, and that the maximum area is 12,500 square feet. And this is how we optimize. For example 2, we're looking at another area volume problem. So an open top box is to be made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box. So we'll do this corner because I seem to have drawn it okay. Remember, squares mean all sides are the same. And so if the length of this side is 36 and you cut a square out of each corner, the new length is 36 minus 2x. Similarly, over here, 24 minus 2x, because you're going to take an x out of each corner. So our new dimensions are 24 minus 2x, 36 minus 2x, and then x if we fold up the box. So this, let's add some color. This here is this length, and this here is this length, and then x, the piece you cut out, actually represents the height of the box. That's kind of how boxes work. So what size should we cut out in order to get the maximum volume? Well, volume is length, 24 minus 2x, width, 36 minus 2x, times height. And let's talk domain restrictions. The smallest square I could cut out is 0, and if I cut out 0, I won't have a box, so that is our minimum. And the most I could cut out is 12. Anything greater than 12, and you're going to get a negative number for one of the dimensions. So my maximum is going to occur at 0, at 12, or where this derivative, once I find it, is equal to 0. So let's simplify the volume one more step so that we can apply the product rule to take its derivative. From here, I recommend that you pause the video and attempt to find the derivative, that's a 36x, and then replay the video and see how I did it. So I'm going to go from here and I'm going to use the product rule. So first take the derivative of the first expression, which is negative 2, times the second equation, and I almost forgot the x again, and then plus the first factor times the derivative of the second factor, which is 36 minus 4x, and then we are going to simplify all this and set it equal to 0. So we've got negative 72x, positive 4x squared. Full distributive property here. We've got 24 times 36, which is 864, minus 96x, minus 72x, plus 2 times 4, which is 8x squared. Combine like terms, and then let's set this up like a quadratic equal to 0. We've got 12x squared plus minus 240x plus 864. Divide everything by 12, and we've got 0 equals x squared minus 20x plus 72. So this would be great if I could factor this. Are there numbers that multiply to be 72 that can add to equal 20? So we might try 9 and 8, 12 and 6, 3 and 24, 2 and 36, or 1 and 72. None of those factors work. This is the type of problem where we need the quadratic equation. So we're going to do x equals 20 plus or minus negative 20 squared minus 4 times 1, that's my leading coefficient, times 72 all over 2, technically times 1. And so if we simplify this as much as possible and get a decimal approximation, we should have the solution to our equation. So I'm going to use my calculator, and I am going to type this beautiful quadratic equation. Although I wonder if I have the problem solver on here. I have poly, maybe. Okay, so we're going to start with 20 plus, I'm going to go ahead and turn that into a fraction. So we've got 20 plus the square root of negative 20, make sure that's in parentheses because it will affect your solution, minus 4 times 72 all over 2. So that first option, I get a side length of 15, but we should recall that the maximum this can be is 12. So this can't be the correct answer. We're going to repeat this process, but instead of a plus, we're going to use a minus. So let's get to that plus sign and change it to a minus sign. And so we find that the solution is 4.7 inches. That is the size of square that I should cut off from my box. 4.7 inches. All right, we're gonna stop part 1 of the video here and meet back in part 2 to finish the remainder of the examples.